This conference will now be recorded.
Everyone, here we have the first question. So today's discussion will be previous year's question from the exam IIT JEE Advanced, and that is from the chapter Chemical Bonding and Molecular Structure. The first question is related to molecular orbital diagram for fluorine molecule. The correct molecular orbital diagram we have to choose for this molecule in the ground state. Okay. Now fluorine is homonuclear diatomic molecule. That means there will be two atoms and both of them will be same atom. That is why it is homonuclear and diatomic. Just like this. That is, in general, if I say it is A2, it may be C2, it may be B2, it may be O2, like this. Now for diatomic homonuclear molecules, one is very important thing that we have to understand, and that is 2s2b mixing. So 2s2b mixing is observed in case of B2, C2 and N2. As you can see here, sigma 2s and then sigma 2h star. So in this zone there is no problem, it is just like that. But when it is the p electron, okay, so BCN, the common point is in both cases, in all these cases, there will be valence electron in 2s and 2p. So regarding 2s, everything is same, because whether it is B2, C2, N2, it is always 2h2. But when it is 2p, for boron it is 2p1, for C2 it is, for carbon it is 2p2, that is valence electron I'm talking about, and for nitrogen it is 2p3. So when it is 2p, now the MO, if you see, pi 2p first, after that sigma 2p. So these two are bonding. This is BB, this is AB, this is AB. AB means anti-bonding. So pi sigma, then pi sigma. Okay. But when it is after nitrogen, if you consider the next molecules, that is, I'm talking about O2 and F2, now the energy levels, there is difference. So regarding this part, there is no change. It is same. But when it is p electrons, now you can see sigma to p, after that pi to p star, and then it is sigma. So in between sigma and sigma star, there will be pi and pi star. But for B2, C2, N2, there is mixing. Why it is called mixing? Because sigma comes in between pi to p and pi to p star. So this is very important. Okay. So up to nitrogen, one type of observation, after nitrogen, another type of observation. If it is so, now our concern is with F2, right? So for F2, if you look at the options, this part there is no change, all are same. So we don't have to bother about this part. But if you consider the 2p part, first there should be sigma 2p, then there should be pi, okay? Then there should be sigma star, pi star, and then there should be sigma star. So between sigma star and sigma, in between these two, there will be pi bonding and pi anti-bonding. So see, which is also same for oxygen. And if that is the so, option C should be the correct option, because in option A, after sigma bonding, there is, after pi bonding, there is sigma bonding. It is not correct at all. Then in the second case, pi, then sigma, but it should start from sigma. Then it is pi, then pi star, then sigma star. Okay, that you can get see only here. We have first sigma bonding, then pi bonding, then pi star, that is pi anti-bonding, and then sigma star, that is sigma anti-bonding. So this is actually matching with the actual molecular orbital diagram for fluorine molecule when it is in ground state. Option C will be correct option. The next question we have here, total 11 species you can see. I3 plus, SiO4 4 minus, SO2Cl2, then xenon fluoride, sulfur tetrafluoride, ClF3, nickel tetracarbonyl, XeO2F2, then we have platinum complex, xenon F4, SOCl2. Total 11 species are there. Now out of this, you have to find the number of species having sp3 hybridized central atom. So you have to check for all these 11 cases whether it is having sp3 hybridization or not. and based on that we will have the final answer as an integer. Okay, so we will draw the molecules one by one. So when it is I3, now in I3 if you are thinking how to choose the central atom, so what you have to do, among these three I, just one I choose as central atom, and if you do so, then steric number if we calculate, it will be half. For iodine it is 7 electrons, that is valence electrons. Number of monovalent atoms attached will be 2, because the other two iodine atoms you have to consider as it is they are monovalently attached. And positive charge, so -1, so you will get 4. That means it should be sp3 hybridization. And how it looks like this: I plus, then 2I, and there will be 2 lone pair. Next one is, so it will be considered as sp3. The next one is SiO4 4 minus. Now for SiO4 4 minus, number 2, central atom is silicon, for which the total number of valence electron, it is just like carbon, because silicon is also from group 14. So the last digit of 14 is 4, that will be the valence electron. So 4, there is no monovalent atoms attached, only oxygen is there, but oxygen is considered as divalently attached, so that is why it will be 0. Positive, negative charge total 4, so plus 4 should be there. So you are again getting sp3 hybridization, right? And how it looks, though it is not asking about it, but still just for extra information I am drawing all this picture. Then we have 3 SO2Cl2. Now for SO2Cl2, sulfur is the central atom, 6 is the valence electron, oxygen is not considered as monovalent, 2 chlorine you have to consider, there is no charge. Again you are getting sp3. Now the number 4. Number 4 is XeF2. Now for xenon, it is from group 18, 8, that is a fully filled, the 2p is fully filled, not 2p, I mean p orbital is fully filled. So it will be 8. Monovalent atoms 2. So 8 plus 2, 10 by 2, it will be 5. That means it is TBP geometry. And when it is TBP geometry, it is basically sp3d hybridization. So it should not be considered as correct option. Now what about the next species, which is SF4? Again sulfur 6, 4. That means it is 10 by 2. It is 5. That means TBP, and it is sp3d hybridization. Okay. And next we have number 6, which is ClF3. Now for ClF3, for chlorine, which will have total 7 electron, and fluorine, 3 fluorine monovalent atoms, 5 sp3d. Number 7 is, okay, nickel tetracarbonate. Now here you will not be able to apply this formula, because that is only for only for p block elements, but nickel tetracarbonate is from a d block. So to answer this question, we also have to, we need the knowledge of d block elements. So here we will just apply the fact that it is actually tetrahedral. Okay, so this should also be considered as our answer. The next one is number 8, which is XeO2F2. 8 for xenon central atom. For oxygen, we should not consider anything, 2 fluorine atoms. So we are getting 5. So for XeO2F2, it is sp3 hybridization. After XeO2F2, PtCl4. Now PtCl4 platinum, whenever it is tetra coordinated, it is mostly observed to have a square planar. Now static number for this type of d block metal complex we cannot apply. So this is square planar. It is not sp3 hybridization, so it should not be considered as our answer. Then we have number 10, which is XeF4. So it is 8 plus 4. Now we are getting 6. So it should be octahedral. That means it is sp3d2 hybridization. The next one, number 11, which is the last one, sulfur, which is 6. And oxygen will not be considered, 2 chlorine will be considered. So 6 plus 2, 8 by 2 is again 4. So this is also sp3. Now we will see total how many species we are getting as sp3. 2, 3, 4. Then 5. So total 5 species there is a central atom with sp3 hybridization. So now we will have all the answers, all the structure also you can see here. So this is 1, 2, 3, 4 and the last one. Fine. So this is tetrahedral. I'm writing in short TD. This is TD. Now in this case sp3d, that means it is basically TBP geometry. This is the triangle and both sides there will be 2 axial bonds. Is again sp3. So this should be the triangle, and above and below of this triangular plane there will be 2 axial bonds. Same thing also here sp3d. Now this is tetrahedral, and this one is again TBP. Then we have square planar, dsp2 hybridization. That is for square planar. Then again we have sp32. This is actually octahedral, but you have total 4 atoms. So the other 2 positions, because it is total 6 coordination, there will be lone pair. But it is sp3d2, and the last one is again tetrahedral. Okay. So answer should be 5, integer. For diatomic molecules, the correct statement or statements about the molecular orbitals formed by overlap of 2 2pz orbitals. 2pz orbital means you have to consider the p orbital which is on the z-axis, because it is specifically mentioned z-axis, right? Now, if you look at the options, the first option is related to sigma orbital formation, the second one is related to sigma star orbital formation. And option C is pi orbital formation, that is pi bonding. Then option D is pi star. So A and B is sigma sigma star, and C and D pi pi star. So first we will consider A and B, where sigma bond, that is sigma bond between 2 2pz. So when there is sigma bond between 2 2pz, suppose this is the z axis. So one p orbital will be like this, another p will be like this. This is the overlapping, that is sigma bonding. When there is phase matching, it will be bonding like this, and when it is anti-bonding, the phase will not be matched. So here we will see the picture for sigma and sigma star. So this is sigma and this is sigma star. So in case of sigma, what happens? There will be phase sign matching. Don't consider it as charge. It is not charge. It is a sign of phase for these 2 lobes of p orbital. So when it is bonding, the phase sign should be matching, and that is why now you can see the electrons cloud, it is larger than the previous picture. But we have to consider, we want to know that nodal plane, not just nodal plane. Option A is saying that it has total of 2 nodal planes. Now we can see there is 2 nodal planes, right? And the planes are already shown here with the square, and this is perpendicular to the screen of the to this screen, right? Perpendicular to the computer screen. So this is xy plane. So the 2 nodal planes, though it is not asking about the planes, but you can see 2 nodal planes are there, xy plane. What about the next statement? Sigma star orbital has 1 node in the xz plane containing the molecular axis. Now what is molecular axis? Molecular axis is basically z axis, because the molecule is on the, that is p orbital is on the z axis. So this axis you have to consider as molecular axis. Okay, suppose instead of 2pz, if it is said that 2px, then x will be the molecular axis. So one node in the xz plane containing molecular axis. Now here you can see 3 nodal planes are we have here, right? Because now the phase sign is not matching. It is either plus minus or minus plus, and now as it is not matching, there will be, now see the lobe size, it is compared to the previous situation, now it is shrink. So there will be total, these 2 nodes are already there before the interaction, and there is new nodal plane is there, but that is again in the xy plane, and it is perpendicular to the molecular axis. It is not containing the molecular axis, isn't it? If you consider these three nodal planes, they are perpendicular to the z-axis. Now we will see pi and pi star. Pi orbital has one node in the plane which is perpendicular to molecular axis and goes through the central of the molecule. So to understand it, again we have to draw the pi. Now z-axis we have taken vertically because now it will be sidewise overlap. It is pi, it is not pi, it is not sigma. So when you are talking about pi and pi star, obviously z-axis now should be vertical. It will be easier for us to understand the interaction. So when there is same phase sign, suppose plus plus, now the electron density, it will be changed like this. And this is the nodal plane, which is perpendicular to the z-axis, and this is xy. So the option is saying pi orbital has one node in the plane, which is perpendicular to the molecular axis. Now xy is perpendicular to the molecular axis z. So this is true. And the second part of the statement is saying goes through the center of the molecule. Now this is the center of the molecule and it is going through that. Okay. So this should be true. What about the next statement? Pi star orbital has one node in the xy plane. Look at the pi star. This node is already there even before the interaction. But now when there is interaction, it is opposite sign. So there will be, this is the new node that we will get. So two nodes you can see. One is already in the xy plane, which is perpendicular to z-axis. And another node that will be either yz or zx. Both will be there. Suppose if I am considering this is as z-axis, then you can write this is as x and y. You have to imagine in 3D. So it will be like this. So this plane is basically the xy plane, and zy plane or zx plane, that also you can understand. So both these planes will be perpendicular to xy, right? Now if I am writing y like this, suppose this is then this plane should be z yz plane or zy plane. Okay, and if you consider this axis as x or sign, I am writing here x, then this plane will be zx. So that is, it is written here either yz or zx. Now the option is saying pi star orbital has one node in the xy plane. That we can see here in the xy plane there is node, and it is also containing the molecular axis. Is it so? No, it is not containing the molecular axis because molecular axis is z and xy is perpendicular to it. Okay. So sorry, I have said it is not correct. Pi star orbital has one node in the xy plane. It is containing molecular axis. Molecular axis is not z. Sorry for that. Molecular axis is not z because see, pi bond formation takes place only after the sigma bond formation. And when we are talking about sigma bond formation, and now the lobes are on the z axis, this is actually molecular axis. But when you are considering pi, the orbitals are always perpendicular to the molecular axis. So now this one you have to consider as the molecular axis, and this is in the xy plane. So pi star orbital has one node in the xy plane, which is also containing the molecular axis. So this is now molecular axis MA. This one, not Z. Z axis will be the molecular axis only when it is sigma. Okay. So sigma orbital has total 2 nodal planes in the first case that we have seen. So this will be correct. Then the second option is saying sigma orbital has one node in the xz plane containing the molecular axis, but there is no plane in the xz plane. It is in the xy plane. All the nodes are xy plane. So this is not correct. Okay. So A and D, these two will be correct. Thermal decomposition of AgNO3 produces two paramagnetic gases. That means AgNO3 we are heating and there is formation of two different gases, both of which are paramagnetic. The total number of electrons present in the antibonding MO of the gas that has higher number of unpaired electrons. So there is generation of two paramagnetic gas that is mentioned here. Now suppose it is X and Y, both are gas. Now among X and Y gas, in both cases there is number of unpaired electrons because they are paramagnetic, it is already mentioned. But obviously in one case there will be higher number of unpaired electrons. First of all, you have to choose that in X and Y, which one is having higher number of unpaired electrons. That you have to choose first. Then you have to consider the corresponding MO diagram so that you can understand how many total electrons are present in the antibonding MO. So here total 3 steps you have to do. First of all, you have to do the step 1 is what is the decomposition product of silver nitrate. That you have to know, because if you do not know the product of decomposition, how we will solve the next steps. So when AgNO3 is decomposed, there is formation of gas X and Y. The second step is among X and Y, you have to choose which one is having higher number of unpaired electrons. Number 3 step, you have to draw the MO diagram and you have to count the total electrons in antibonding MO. So this is the reaction of decomposition of AgNO3, where silver metal is we are getting nitrogen dioxide gas and we are getting half oxygen, but oxygen is produced. Balancing is not important. Now in NO2 there is 1 unpaired electron and in O2 there is 2 unpaired electrons. Now to understand in O2 how 2 unpaired electrons are present, without drawing MO diagram you will not be able to understand. So for O2 just draw the MO so that you can understand how the unpaired electrons are there. Because if you simply consider the oxygen molecule, you will not be able to understand the unpaired electron. Because we know there is 2 lone pair for each oxygen and there is bonding electron like this. So from this picture it is not possible to understand. But drawing picture for NO2 like this, you will be able to understand the unpaired electron. How? So for nitrogen, total 5 valence electron, right? So 1 oxygen is attached by double bond, and that means nitrogen is using 2 electrons for these 2 bonds with oxygen. Now another oxygen is attached by coordinate bond. Now coordinate means a bond means what? Coordinate bond means where both the electrons are coming from the single atom. Now I will write the electrons of nitrogen with red color. So 2 electrons of nitrogen out of 5 valence electron used up in double bond formation. 2 electrons are also used up in coordination bond. There is a negative sign given on this and positive sign is given on nitrogen. So overall it is neutral, but whatever. There is a double bond, there is a coordination bond. And the 5th electron is basically this lone electron. And this is the 1 unpaired electron. So now you can understand in NO2 there is just single unpaired electron. But for O2, now this is the MO. 1s2, 2s2, 1s2, 2s2, 2p4. So 2s part even if you 1s part even if you do not draw, it doesn't matter. This part also not required because these are fully filled. So it doesn't matter whether you during bond order calculation or unpaired electron whether present or not. This part you don't have need to draw. This is simply wastage of time. Just focus on the 2p part. So when it is 2p part, here total 4 electrons, here also total 4 electrons. And remember 2s2p mixing is not present. So first there is sigma bonding, then pi pi star, then sigma star. Now 4 electron, total 8 electron. So 8 electrons if you place according to Hund's rule, now you will be able to understand 2 unpaired electrons are there. Okay, so second step is already done. Now come to the third step. In the third step, you have to finally calculate the total number of electrons present in anti-bonding orbital. So total number of electron present in anti-bonding means these two should be considered, right? And here, even if you do not draw these two parts, we can easily understand that as it is fully filled. So 2s2, total 4 electrons for 2 oxygen. So obviously 2 electrons will be here. 2 electrons here. 2 electrons. So total 6 electrons in anti-bonding. So when you will calculate the total electrons in antibonding, now 2s 1s you have to consider. But I was saying that when you are lacking time in exam hall and you just have to know with how many unpaired electrons. So this fully filled part, even if you do not know, it doesn't matter. But when you will answer question like this, total number of electrons you have to count, then obviously don't forget to consider these two also. Okay, so answer is 6. Consider following compounds in the liquid form. So all the compounds are given. You have to consider in liquid form, because see, some of the molecules given, they are normally not always in liquid form. Just take the example of O2. It is not liquid, but you have to consider in liquid form. Why? Because if you look at this picture, there is a burette and as if some liquid is dropping. So it is not possible with some gas. So it is possible only with liquid. So you consider all of them as liquid. Now when a charged comb, a comb which is already charged, suppose with electrons, is brought near their flowing stream of all these liquids, how many of them show deflection? Now deflection when possible, a charge species is there and you have another charge species, then only the question of deflection, not another charge species. I'm trying to say another species where some polarity is present. So if in this liquid there is some polarity, then only it will be attracted towards the charged comb or any other charge species, right? So the question is basically asking indirectly, out of these molecules, which molecules will be having some polarity? That means which molecules will have dipole moment. Okay, so it is simply asking out of these molecules, how many are polar, how many are non, and that you can understand by understanding the dipole moment. Okay, so one by one we have to do the dipole moment checking. So for O2, it is simply homonuclear diatomic. It will not be polar, right? Then HF, yes, this will be polar because H and F, there is huge difference in electronegativity. Now water also, it is having bent structure like this, so dipole moments are not cancelled, so this should also be polar. Then ammonia, the same thing, there is lone pair in this position, but overall a dipole moment is not cancelled, there will be some net dipole moment. Then for H2O2, now H2O2 is having very specific type of structure, open book type of structure, where in one page of the book, one side of the book, there is one wedge bond, another side of the book, another wedge bond. So see, this is open book type of structure, whether H2O2 in gaseous state or in solid state, even if it is true for liquid state. So both extreme gas, solid, it remains in this structure. There is slight difference in the angle, but otherwise overall structure is same. So here also it is not symmetric, there will be some polarity. CCl4, now this is symmetrical tetrahedral, and here bond, that is one dipole moment will be cancelled by the other bond's dipole moment. So here it will be non-polar. Chloroform. Now chloroform is just like CCl4, only difference is you have now one hydrogen instead of one chlorine. So this will be having some dipole moment. Then we have benzene ring, and at last we have chlorobenzene. Now out of chlorobenzene and benzene, obviously in chlorobenzene, chlorine is electron withdrawing. So if it is 2 chlorine in para position 1,4, there is a chance of cancellation. But for monochlorobenzene, there will be some dipole moment, right? So how many of them show deflection means how many of them will be polar. So here non-polar are basically only 3, but rest of them, that is 6, total 6 plus 3, 9, out of 9, 6 are there will be deflection. Okay, so these are the answers, integer question. This question is very interesting and you have to read it very carefully. So many things, so many steps are there that we have to do one by one. This is a very good question, and to solve this question we also apply the first unit, that is atomic structure. That information also we need, and one formula is required that we normally use in physics, not chemistry. So first try to understand what the question is asking. You can see a figure here, right? And there is a potential energy in kilojoule per mole, that is in the y-axis, and in the x-axis there is internuclear distance, which is small d, an internuclear distance between two hydrogen atoms. So this is basically the energy diagram for hydrogen molecule formation. Now hydrogen molecule formation means when the two hydrogen atoms, they are far from each other, there is no bonding. Now gradually you are bringing the two hydrogen atoms close to each other, and there will be a certain distance where there will be minimum energy and bond formation will take place, and that minimum energy is this position. So if you draw a line here, then this particular distance is its bond distance, because only at this position where the energy is minimum, energy minimum is clear from this picture, that is the bonding distance. But the question is not asking about the bonding distance, it is asking the value of energy at this point. And at this point, the two hydrogens are basically apart from each other, they are not in the bonding distance. And two hydrogens, when they are somewhere here, now the D value is very low. That means they are very close to each other. There will be huge amount of repulsion between electrons, negative charge, between two nucleus, positive charge. But this is a distance where the question is based upon on this distance. This is a distance where hydrogens are far from each other. Now what it is asking? The figure below is the plot of potential energy versus internuclear distance of H2 molecule. Now, potential energy means already the energy which is stored inside the molecule, that we have to find. Hydrogen molecule in the electronic ground state. What is the value of net potential energy E0 value as given in the figure in this unit when D is equal to D0? That means at this particular position you have to find it. And at this particular position, what is so special about it? At this position, the electron-electron repulsion, that is a negative charge repulsion, and nucleus-nucleus repulsion, that is positive charge repulsion. This is negative, negative, this is positive. Both are absent. And it has to be, because the hydrogens are far from each other. This is such a position. Now, as reference, this is the question end. Now, there is some extra information you have to keep in mind. As reference, the potential energy of hydrogen atom is taken as 0 when its electron and nucleus are infinitely far apart. So why this line is mentioned, how it will help us to answer the question. Forget about hydrogen molecules. Suppose you have only one hydrogen atom, and when one hydrogen atom, and I am saying its potential energy is 0, it is possible when its electrons and nucleus infinitely far apart. Though that is not possible, but when potential energy is 0, that should be the condition. But that is not the actual case. In hydrogen atom, what happens? Electrons are close to the nucleus. So when they are close to nucleus, they are actually negative. So the final answer that you will get, that is actually negative. So the potential energy between electron and the positive charge in the nucleus, it is negative, means if you want to remove the electron from this attractive field of positive charge, you have to apply energy. When potential energy is negative, that means you have to force the process. Then only you can remove the electron. So this is the meaning of this statement. And Avogadro constant is there because you have to calculate the energy per mole. So this number you require, right? So here the formula that we will use, that is the physics formula, and that formula is energy, sorry, not energy, is actually force, or better, sorry, it is energy actually, not force. So this is Coulomb's law, and that is small k into Q1, Q2 divided by R square. So in this case, this k value, which is called Coulomb's constant, that value is, though it is not given, but that value is 9 into 10 to the power 9 in meter square part c square, that is Coulomb square, that is the value. And here Q1 charge, that is actually the charge of electron or charge of proton, both are same, only negative, but the numerical value is same. This is Coulomb Q1, which is also true for Q2, same. And the R distance that you will consider here, that is actually the Bohr's radius. Remember the formula? 529 multiplied by n square by z. But for hydrogen atom, n value ground state it is 1, n value is 1, z is also 1. So R will be simply 0.529 angstrom. If you convert it to meter, it will be 10 to the power minus 10 meter. So we will put all these values here. So Q1, Q2. So what we are trying to do, we are trying to find the potential energy between, just take one hydrogen atom. This is the nucleus and this is somewhere the electron. So this distance is R, which is 0.529. This is the center, which is for proton. So charge between two particles, when you consider potential energy between two particles, we use this formula, where R is the distance between the any two charged particles. In our case, it is proton electron, but it is applicable for any two charged particles. R is the distance between these two charge. In our case, R is 0.529 angstrom. Q1, Q2, both values are same for proton and electron. And K value, it is a given constant, which is called Coulomb constant. Now we will put all these values in this equation and we will calculate what is the E value. So that we will do in the sorry. So here 9 into 10 to the power 9 multiplied by 1.6 into 10 to the power minus 19, and there is a square. And the R value, remember, 0.529 multiplied by 10 to the power minus 10. So now the unit you will get in SI and it will be in joule, but from joule we have to convert it to per mole and then kilojoule. Now the value that you will get, it will be 43.99 multiplied by 10 to the power minus 19. If you bring this power 10 above, it will be 19. Total 1 minus 19 will be cancelled. You will be left with 1. Now this energy, we will change it to kilojoule. And for that, what you have to do, you have to multiply with 10 to the power 3. 10 to the power minus 3 from joule to kilojoule. But it is only for one atom. But if you do it for Avogadro number of atoms, that means per mole you will get. So you have to multiply it with Avogadro number. Okay. So finally, if you multiply all this, you will get, there is actually negative sign. But this is only for one atom, one hydrogen atom. This is not the final answer. You have to do it for hydrogen molecule. Though molecule is not formed, but still there is 2 hydrogen. You have to consider it for 2. So again, it is multiplied by 2. So finally, you will get 2623.02, 5246.04 kilojoule per mole. So this should be the final answer. And the significance of this negative value, remember, as when electron and proton, they are far apart from each other, if at that condition it is 0, that means when it is close to the nucleus, now the energy will be negative. So the significance is a negative value for the energy. It means you must supply energy to the system if the electrons is to overcome the attractive force of the nucleus and escape from the atom. That process requires energy, right? So that is why this value will be negative. Each of the following options contains 4 molecules. Identify the option where all the molecules possess permanent dipole moment. It may be more than one option correct. Fine. Now BeCl2, if you consider the central atom B, if you know the structure already, it is fine. It is actually linear like this. But you can also calculate its steric number. For B, valence electron will be 2. two monovalent atoms attached, half of it, that means it is a 2 coordination, so it will be linear like this. Okay, so it is not polar, the bond moments will be cancelled. Then we have CO2. Now for CO2, this is also linear. For BCl3, steric number you can calculate. For boron it will be 3 monovalent atoms, so 3 means it will be having planar trigonal structure like this. Now again, it is a planar molecule and all the bond moments, they will cancel each other. The directions will be towards chlorine. So this will be not, it will be non-polar. So you have to find those set where all the molecules will be having permanent DM. Now CHCl3, it has dipole moment that we know. What about SO2? SO2 is bent structure like this. You can simply calculate steric number. Because of lack of time, just doing it fast. Then C6H5Cl, that also we know there will be polarity. Then H2SE, it is just like water molecule because selenium is also from group 16, right? So it is having polarity, there is polarity, there is polarity. BRF5, if you calculate steric number, for bromine it is 7 and for 5 fluorine. So 7 plus 5, 12 by 2, it is 6. That means it should be octahedral, but one position there will be lone pair. But overall the molecule is not symmetric, so there will be some polarity. So this option is such an option that you can choose. Come to option 3. BF3 is non-polar. Now O3, it is bent, there will be some polarity. But for SF6, if you calculate steric number, you will see it is basically octahedral. And when octahedral with all the bonds symmetric SF bond, so there will be no polarity. Okay. Then XZF6, for xenon it is 8 plus 6 divided by 2. So it is 7, though its structure is actually distorted octahedral. But see, even in details, all the options, all the molecules, if you do not do, then also it's okay, because you have to choose those options where all the molecules are having some permanent dipole moment. So in any options, if you like BF3, it is non-polar, you already know. There is no permanent dipole moment. So you can easily cancel this. You don't have to even move to SF6 or XZF6. One molecule, no permanent dipole moment, it is enough to cancel the option. I'm just doing it for extra information, but 3 options you can cancel. Also in option 1, we already know the CO2 symmetrical, there is a linear structure. So just on the basis of CO2, we can cancel this option. Option 2 is correct. What about option 4? NO2 is having bent structure like this. There is a coordinate bond, remember, with unpaired electrons. So there is permanent dipole moment. Ammonia also. POCl3. Calculate steric number. For phosphorus, it is 5. For 3 chlorine atoms, oxygen is not considered. It is 4, that means tetrahedral. So it will also have permanent dipole moment and chlorobenzene. So this option also, all the molecules are having permanent dipole moment. So these 2 options out of 1, 2, 3, 4, 2 and 4, where all the species, all the 4 species, they are having some permanent dipole moment. So that is why these 2 options will be correct option. We have very little time, we'll try to solve it. Compounds with 2 lone pairs of electron on the central atom is or are. So BRF5 you have already seen in the previous diagram. There is 1 lone pair only, right? So this is not our correct option. Then in ClF3, if you calculate steric number, for chlorine it is 7, 3. So it is 5, that means it is having TBP structure. But in TBP structure, all the 5 positions, you will not find fluorine. So total 3 fluorines will be there, and rest of the 2 positions you have to place lone pair. So this should be correct option. Then what about xenon F4? Steric number 8 plus 4, it is 6. That means octahedral should be its structure, but you have only 4. So rest of the 2 positions there must be lone pair. This is also our correct option. What about SF4? SF4 steric number, sulfur is 6, 4 fluorine. So you are getting 5. That means it should be TBP. But all the 5 positions, there is not fluorine we cannot place. So one position there must be lone pair. So there is actually one lone pair. This is not correct. The middle two options, that is B and C, these two are basically the correct option. Okay. We have one more problem, but okay, quickly we can solve it. Assuming Hund's rule is violated, the bond order and magnetic nature of diatomic molecule B2. So B2 is having this type of structure, this type molecular orbital. Its valence shell configuration is 2s2, 2p1. So just focus on this part, that is enough. So 2p, 2p, one electron from both sides, and there is mixing of p and s. So that is why pi first, then sigma, again pi, then sigma. So here you can understand the magnetic nature. There is unpaired electron, so it will be magnetic nature of the diatomic molecule. Okay. And what about the bond order? Hund's rule violated. Under that condition, it is asking about the magnetic nature. So Hund's rule what says? There must be some placing of unpaired electron, then only you can do pairing. But here we will not maintain Hund's rule. So both the electrons, instead of writing like this, we will write both the electrons in the same 2p. So that is why now it will be converted from para to dia. So it should be either this among any of these two options. What about the bond order? Total number of bonding electrons minus total number of anti-bonding electrons divided by 2. So total bonding electrons 2. 2 minus 0, because in anti-bonding you do not have orbital, you do not have electron. So it should be 1. And if you are thinking why I have not considered this part to calculate bond order, because that is not required. It is always cancelled. Sigma star 2 electron cancelled by this. Sigma star 1 is cancelled by sigma 1. So when calculating bond order as fully filled orbital, even if you do not count, doesn't matter. So for simplification, I have considered only the bonding orbital in 2p. Bonding electrons in 2p, which is 2. No anti-bonding electrons, 0. 2 by 2 is 1. So 1 and diamagnetic, this should be the correct option. Okay. Thank you for listening. We'll close the session here.